We have now started to talk about the algorithmic approach, namely how to train neural networks. Neural networks is given by parameters, and of course we want to find the parameters or change the parameters in such a way that the neural network is doing what it is supposed to do. Okay, and we started with linear regression, and we checked that in linear regression, when in principle we have formulas for describing what the best solution in this case is, we also can do this via gradient descent. Okay, and now we want to go, let's say, one step or one layer beyond a linear regression, and we consider our one hidden layer neural network. So this is, we consider now our neural net, which is a function which is given that I'm multiplying w with sigma of w1 divided by square root p times x. So x is now my data vector. I could also write it as a matrix, so this is little x, then this here should also be a little x. And we have two matrices w1 and a vector w. Linear regression was that w1 is given somehow at the beginning, and we just want to optimize in this w here. Okay, but now we want to train all parameters, also the w1. Okay, and maybe I rename things a little bit, in particular because I have two w's here. This is a bit confusing. So maybe I call w, and this w here, this is a row vector, and maybe I will now denote consider all vectors as a column vector. So if I want to have a row, then I write it as a transpose. So I write this as a transpose of something, and let me call this A. And for the moment, this scaling, I don't care about this. So maybe later we come back to this. So I denote w1 divided by square root of p. I now denote just by w. Okay, so there are no several w's there. Okay, so this here is now my function f of x. So I'm just writing it. It's the same thing, but this here I'm writing as A transpose and then multiplied with sigma. Sigma is my given nonlinearity of wx. Okay, and so the dimensions. So x is our data vector, which is usually p-dimensional. Then this w here, this is the random features or our feature matrix, which maps the p-dimensional vectors into m-dimensional space. So this w here is m times p matrix, and then I'm going back, and my result is always a scalar. I only consider the case where I'm going to R. So I take now linear combinations of the what I get here with this here by multiplying it. So A is here in Rm. So A transpose is a row, and I'm just taking essentially the inner product between this guy and the output here. And of course here I'm applying my nonlinearity. So I'm getting here a vector in R to the m, and then I apply entry-wise this nonlinearity. So I still have a vector in R to the m, and then I multiply it in a scalar product with this. Okay, and of course this is a function which depends now on this A and this W. And usually, or very often, I mean the parameters I denote by theta. So theta is a collection of all parameters. So this depends on the parameters, which I just denote by theta, and this is the collection of my vector A and my matrix W. Of course, the coordinates of A, so A has m, A is in R to the m, so this has m components, and W as a matrix, this has m times p components. So this is a collection of m components of A plus m times p, the components of W, real numbers. So this is a m plus m times p dimensional vector. Okay, so again, I put all the theta, the elements, I consider it as a vector. Good. Okay, so that's my function. And of course, I want to train my function in such a way that it should do something which is prescribed. And this prescription is given by doing observations. So I'm, for some values of x, I measure what the outcome is, and I want a function which really does this. So what I'm given are, let's say, n observations. So given n observations. So this means I have n x's. I call them x1 up to xn hat, and then I know what the corresponding y value is for them. So my observations consists of pairs x1 hat, y1 hat, up to xn hat, yn hat. Okay, so those are guys. I mean, the x's are, of course, my datas, which are p-dimensional, and the outcome, the y's, are just real numbers. Okay, and what I want, so given those n observations, so we want theta such that with those parameters, the function f theta of this specific form really satisfies that f theta applied to the xk hat is the yk hat for all observations which I have made up to n. Okay, so I mean that's what I want of my function. It really should reproduce the given values for those n points, and otherwise, I mean, it should be as nice as possible in between. But of course, okay, so if I have many parameters, there's no unique solution to this. Okay, in linear regression, we said, okay, we know somehow what is the best solution, but here we don't know. I mean, I cannot give you a formula here, what is the best solution for this. I even don't know what maybe best means exactly. But so we just do gradient descent. So we just initialize somehow, choosing a and w, and then we just, okay, then of course we have a function which does not satisfy this. Yeah. In most cases will not satisfy this, so we try to improve the parameters. Okay, and so this means we have to measure somehow the deviation from the situation which we want, and then gradient descent should improve this situation. Okay, so we measure the deviation from this. Yeah, by a loss function. Which just tells us, good, that we don't have this, and of course the loss function should be something which is positive. I mean, the loss, we want that the loss is equal to 0. If it's not 0, it should be positive, so that if we can optimize it by looking for a minimum of it. Okay, so we consider a function which we call a loss function, which I denote usually by an L, and of course it depends on theta. It depends on my function here, but the function depends on theta. Okay, and what I'm checking is, and maybe let me put a 1/2 here, which is convenient later. So I'm taking f theta of xk hat, and I check how far or how close this is to the yk hat. Okay, and of course, if it is equal, this is 0. If it is not equal, then it is plus minus. Okay, plus minus in the sum is not good because we want to minimize all of them. So I take the square here. That's the simplest way of doing it. So I take the L2 error here. Okay, so I'm just checking. I'm taking the sum of the errors which I make. Good. Okay, and so this depends on theta, and I want now to find a good theta. And so we do this now by gradient descent idea, which just says, okay, we want to minimize this function here, and if we have a theta which is not the minimum value, then we go in the direction of the gradient with respect to theta. This should improve then. This should us give a smaller one. And that's what gradient descent is doing. And that's what we are doing here. So we minimize this. And I mean, in the over-parameterized case, if you have many parameters, then usually we can find thetas for which this is equal to 0. If you only have few parameters, then of course maybe that's not possible to find in my class a function which does this exactly. but then I mean what you do in a least square, at least you try to make the error as small as possible. Huh? Okay, but our concern is usually the over-parameterized case. Our linear nets have, our neural nets have many parameters so that we are able to really get here 0. Okay, good, but so we want to minimize this, yeah, by changing our parameters to theta, yeah, by doing a gradient descent. Yeah, and what does this mean? So this means I start somewhere with thetas, usually choosing it in a random way, and then I improving it by changing it in each time step or each iteration step by adding to the thetas which I had before the gradient of this loss function. And of course I should have here learning rate or step size which tells me how much I change it in this direction, and of course I take here minus because this means I should increase it. The gradient shows in a direction where this thing increases. I want to decrease it, so I should go in the opposite direction. Okay, and then I take the gradient of my loss function of the parameters which I had in the step before, and the gradient is with respect to the parameters. Okay. Yeah. And so I'm writing my parameters as one big vector. And this gradient here is, of course, also a vector which takes the derivatives, the partial derivatives of this guy here with respect to all parameters which I have there. So this is a collection of partial derivative with respect to the entries of A and with respect to the entries of W. Good. Okay. So that's what gradient descent is doing, and maybe it's nicer to write this in a more differential form. So maybe let me rename this by really looking at this on theta as a function of time. I mean here I say the time is just integer, it's just the steps I'm doing, but maybe I'm really say I have here time, and maybe the step I'm doing in a small time. So maybe I just rename this here. And then I say that it's theta, and I'm adding here a small time step. This is here theta t, and then what I'm doing here should also be proportional to the time of this gradient. Yeah, okay, and now you see what I have here. If I bring this on the other side, theta of, maybe, so this means I have theta of t plus delta t minus theta of t, and then I can divide it by delta of t. So this is minus eta, the gradient of my loss function at the time t before. Okay, now you see why I have maybe changed it in this way. Now I send this delta t to 0, and then I have here a kind of differential equation. So I just prefer it to write these discrete things, of course. The algorithm is doing it in a discrete way, but you can think of this as a discretization of this differential equation, and maybe it's nicer to write it down, and maybe also nicer to argue. So I mean I'm now sending this delta t to 0, and then of course I get a differential equation for the time change of my parameters. So what this gradient descent is doing in a discretized way is essentially described by that the derivative of my parameters is given by minus eta times the gradient of the loss function at the time t, and the gradient of course with respect to the parameters. So that's essentially what gradient descent is doing if I formulate it in a continuous way. And maybe in the following, I also write maybe sometimes instead of theta of t, I also write theta with a subscript of t. So that's just, maybe at some point it's nicer to do this. Okay, so now my theta is changing, but of course theta is only a tool for describing my f. So what I really want maybe is to see how does f change, because what I want is to understand f. F is given in terms of my parameters. So if the parameters are changing, those guys here, then of course this f is also changing. And so maybe let us see what can we say about the change of f. because I mean, of course, at the beginning f is not good, but it should improve under the time evolution, at least that for this data, this x hat data, my observations, I really should converge to this guy. And then, of course, we would also like to understand what does it for other x's in between, interpolated guys. Good. Okay, so but let us now see what this time evolution of the parameters means for the change of my function. So this change in theta, of course, induces a change in my function, and the function will thus also depend on the time, because the function depends on the parameters, and the parameters depend on the time. So I have a function, and maybe I put here, I denote this as f sub t, which is just f of theta of t. Okay, and of course this is our main concern. That's what we really want to, that it behaves in a nice way. And the change in the parameters is of course driven by behavior which we want to have of f. Good, okay, but so now let us see what can we say about the time change of this f. Okay, so so if I take now the derivative of f of t applied to a point x, I mean f is a function of my p-dimensional vectors x's, and this will also change in t. Okay, I mean this here by this is of course just I take the derivative of the function given by the parameters which depend on t at a point x. Yeah, and now of course I know how the parameters change, so I can now use the chain rule, of course. So I mean this derivative of f with respect to t comes from the that f depends on the parameters, and then the parameters depend on t. So by the chain rule, I have to sum over all partial derivatives of my function with respect to the parameters, all the parameters, and then multiply it with the change of the parameters according to t. So this by the chain rule is I have to take the gradient of my function f of theta with respect to theta. So that's a collection of all partial derivatives of the function f with respect to the parameter. Okay, and then I have to multiply it with the change of the parameter with respect to t. So this is multiplied with d theta of t divided by t. And of course, this is an inner product. I mean, a chain rule. So I mean, this is the vector consisting of partial derivatives with respect to one of the thetas multiplied with the derivative of the corresponding theta with this. Okay, so this is inner product, and if I write all my vectors as column vectors, then also the gradient now I should be a column vector, and to have here an inner product I should take here the transpose. Okay, but again here I mean the gradient, here I also mean with the gradient a row vector, a column vector. Okay, so this is the inner product between this and this, which is just a chain rule. Good, okay, so that's, and of course we know something about this, so we should plug this in and see what we get from this. Yeah, so what I have here, maybe I continue better on the top. Okay, so this is okay, this guy here is minus eta times the gradient, so I have here minus eta, and then I have this first gradient, which is the one which I have here. So this is the gradient with respect to theta of f of t x transpose, and then the derivative of d theta with respect to dt is this minus eta times the gradient of this guy here. So I have here the gradient of L with respect to theta at the time t. Good. Okay, and now of course we should think what is the gradient of this loss function. And the loss function of course is the sum of the squares. So we take the gradient with respect to theta. So I mean, And this loss function, I mean, this is of course dependent on those x hat and y hats, but they are given from the beginning. They are fixed. I mean, this is really a function of the thetas. This is f of xk hat. This depends on the thetas. And so we want to see what is the derivative, the partial derivative with respect to the thetas. I mean, those guys here are just fixed numbers from the very beginning. Fixed. They are not changing in time. Okay, so what is this? So this derivative of my loss function of the parameters at time t with respect to theta. Yeah, so this is, okay, and now you see why I have this 1/2 here, because I take the derivative of the square, so I get down a 2. Okay, but I have this sum. Of course, I'm summing here over k's, which are running from 1 up to n, for my n observations. Yeah, so I'm summing here from 1 up to n. Yeah, maybe let me first write it down. So I get the gradient of, so for each k, I get the gradient of this f theta of xk hat minus yk hat squared. And I had the factor 1/2 here. Okay, and now I really do the gradient here. So this is the derivative with respect to this guy. So I take the gradient. So what I take here is the collection of all partial derivatives with respect to any of the parameters which I have here. So what I get here is a vector of all the partial derivatives. Okay, and for each of them, of course, I have here the derivative of the square. So I take the what is it? Chain rule. Okay, but in this case, I mean, I have here a function which goes to R. So this is really something in R. I have here a function which goes from what? From my parameter space to R. Okay, and so I get the outer derivative. So this is just f theta of xk hat minus yk hat. And the 2 comes down, so it cancels this 1/2. And then I have to multiply it with the derivative, with the inner derivative, with respect to the corresponding theta. So I take the derivative of this guy with respect to theta. I take the collection of all partial derivatives, so I take the gradient. And of course, the yk hat doesn't depend on the parameter, so I just take the gradient of this guy. So I take the gradient with respect to theta of ft. Maybe I write here ft at xk hat. Good. Okay. Yeah, so that's what I get. And so now let us plug this in there. So what do we have all together? We have that the dft of x divided by t. So this is minus eta. Then I have this sum, which maybe I take at the beginning, the front, so 1 to n. And then I have the first gradient of f coming from the top formula here, from the very beginning, f theta of ft of x transpose. And then I get this term here from the gradient of the loss function. So this is this gradient here. This is the gradient of theta f of t xk hat multiplied with this difference, f theta of xk hat minus yk hat. So this gradient here is a vector. This guy here is just a number. So I can move this on either side as I want. This is just one-dimensional. Good. Okay, and so now you see, what I have here essentially is a time evolution which is driven by this object here. Okay, and so it's what I have here is a kind of kernel. I mean, I'm applying this to this function here, and I'm summing over this variable here, and the output depends on this variable. So I have here an object which you can say depends on two variables, so this guy, and I'm acting with this guy here in a form as I do it usually with a kernel. I mean, a kernel is something which depends on two variables, and usually you integrate or you sum over one of them, and the output depends then on the other. And that's exactly what I'm doing here. So essentially this here is an object which somehow governs this time evolution, and this is a kernel, and this is a very important kernel in this context, and this is usually called a neural tangent kernel. So this is an object which has become quite prominent in the last years, and yeah, so let me maybe give a name or notation to it, and then we have to understand it a little bit better. So I define let me call it K. And of course, I mean, this object which I have here depends somehow on the time, because I mean, I am taking here the gradients of this function f of t. So maybe I should put also the time here. So I denote it kt, and it depends on two vectors. Let me call them x and x twiddle. So here the first one is x, the second one is xk hat. But I mean, I can define it arbitrarily, and so you see it's just a product of the transpose of the gradient evaluated at one argument times the gradient at some other argument. So this is just the gradient of f of t x transpose times the gradient of f of t at x twiddle. So I'm just taking the gradient with respect to theta at two arguments, x and x twiddle. Okay, and this guy is called a neural tangent kernel. So it's a kernel. It comes from these neural networks, and in a sense, it's the tangent. It's the linear approximation in things I'm doing here. Okay, so this is called neural tangent kernel, and it was introduced, I mean, about 5 years ago, and since then it's a very popular and important object in this context. So it was introduced by Jaco, Gabriel, and Hongla in 2018. Okay, and of course, I mean, in principle, this guy here is a probabilistic object which depends on time. I mean, it is of course given in terms of the parameters which I have there, which are probabilistic, and of course they evolve in time. So this is a probabilistic object evolving in time. Okay, and unless we don't know anything more about it, I mean, it's not very useful, because it's just a notation for an abstract object, and here we have just a compact way of writing our time evolution. But if we cannot say more about this guy here, then this is not useful. I mean, we cannot get more information out of it. Okay, but the point is that actually somehow, usually one can get rid of the probabilistic and one can get rid of the time dependence. So namely, it has turned out that actually, first of all, if we go to our usual limit, the large width limit, that m goes to infinity, then usually we get concentration, and this means also here that this kernel here also converges to a deterministic object. I think from our experience with concentration, this should not be too surprising. That's something which probably we could believe. So I mean, so the point is here, so that in the large width limit, I mean that's the width of our random matrices, that's the m, where m goes to infinity. This is, okay, so first of all, it is deterministic. Let's say at initialization. I mean, we have this at time t equal to 0. And there it is, okay, it is given by our random matrices, and in some way, and it converges to a deterministic object. So this essentially is concentration. Good. Okay. But then maybe the more surprising thing is that actually, so I mean, in principle now we have a deterministic object, but it still should evolve in time. Okay. But it, in many cases, in this setting, it's becoming independent of time. So actually, it's a constant object. So it is given by something at initialization, but then it does not change anymore. Okay, so maybe this is the more surprising thing. So at the moment, maybe this is not so clear, and maybe at some point I might come back to this. But at the moment, let us just take this as given. So this becomes independent of time. And maybe that's one of the main results here, and which justifies really to introduce this object, because then you really can work with it. Okay, and then maybe we have here something which is independent of time. Then you see that we have here kind of exponential, or we have a differential equation which goes with exponential decay. So this means we should exponentially decay to something, but this exponential decay goes somehow with the eigenvalues of this object. So if we would have eigenvalues which are equal to 0, we might also have problems. But this usually does not happen. So usually one can also see that this kernel here stays away from 0, which means all its eigenvalues are positive, and we have decay in all directions. So that's also an important thing. So k stays away from 0. I mean it's positive, or it's positive semi-definite, because it's something times its transpose, so it's a positive thing, but it could have eigenvalue 0, but this usually does not happen, so it stays away from 0. And maybe more general, one can prove something that k is bigger than delta times the identity, for some delta strictly bigger than 0. Okay. Yeah, maybe I will also come back to this at some point. I mean, this is also not so clear at the moment. So those are just statements which have to be proved, and have been proved rigorously, but they are not so straightforward. Good. Okay. So, but with this now, now we can go back to analyzing this equation and just write down what is the solution of this. But I mean, if this here is time dependent, then of course we don't know what to do. We could write down maybe a formal solution, but we wouldn't see so much. But if this here is a constant object, then this here is just essentially the differential equation of an exponential function in matrices and vectors. But we can really write down something for this. So let us do this in the following. But maybe let me also write what I have here instead in the vectors, also in the data matrices. So in particular, I mean here on this side. Usually, I mean, I have my data observations, so I have n of them. Each of them is a vector, but usually we collect them in a matrix. And then instead of writing for each vector our equations, we can collect them into one equation, which is of the same form. We just have to replace the vector by the matrix, which just is the combination of all the vector equations. Because the structure of the equations, matrix multiplication and so, is really compatible with this. So if I multiply a matrix with another matrix, this is just a collection of multiplying the matrix with each column vector in the other matrix. And the outcome is just the outcome of all those matrix multiplication on the vectors. Okay, and this also goes over to this setting. So maybe it's also nice to write this in this setting. So namely, note that if I collect, let's say my observations, the x1 hat up to xn hat into our data vector, and also the y results in a corresponding vector. So namely, I'm writing x hat as the collection of x1 hat up to xn hat. So each of them is a p-dimensional vector. So what I have here is a p times n matrix, and the y hats I'm also collecting into a vector y hat. So this is a vector consisting of y1 hat up to yn hat. So each of the y hats is just a number. So the y hat is just an n-dimensional vector. Okay, then I can write this equation here for the time evolution, maybe also in the following way. So let me write it again. So I have df t of x with respect to dt. This is minus eta. I have the gradient of theta ft xt transpose. I mean, this here doesn't depend on k, so I can take it out. And then I'm left with the remaining things where I'm summing over k. So I have here the sum over k from 1 up to n, the gradient of f theta xk hat multiplied with ft of xk hat minus yk hat. So that's just writing down the same equation. I just have moved the summation over here. And I mean this here now. So here I'm summing over all the k's. This can now be written as the gradient of ft. And now I'm putting here in my data matrix, this x matrix, which is just a collection of all these xk vectors here, and I'm multiplying this with ft of x hat minus y hat. Because, so what I'm doing here is, I mean, I have now here a vector, and I have here a matrix, and I'm multiplying the columns here with the rows here, and this is exactly the product with which I have written down here. So I'm summing over this is exactly the same as I'm doing this in this matrix language. Because I'm taking here the inner product between the entries from here and the entries from here, but the entries from here are actually vectors. Okay, and so if I now put in here one of the other x's, and then I can also amplify this x here to the data matrix. And thus, I can also write it that dft of my matrix x hat with respect to dt is minus eta, this gradient, the gradient of f of t, but here I have now this data matrix transpose multiplied with this guy here, gradient of ft x hat, and then multiplied with ft of x hat minus y hat. Okay, so this is just lifting the whole thing from vectors to the collection of our data vectors, which is this matrix X. Okay, so I mean this here is now a collection of equations, and I mean I have one equation for each column of this x hat here, but this is then just a vector xl hat. Okay, so it's just a compact form of writing this down. And now you see essentially that we have here an exponential convergence of this quantity to this quantity, or maybe to put it another way, this quantity here should go exponentially to 0. And maybe the best way to see it is that we also amplify this side here to a derivative of this side, but of course the y hat doesn't depend on time, so we just can add it on the other side. So let me just write, instead of looking on the time derivative of ft of x hat, let me look on the time derivative of this quantity here. Because this quantity is the one which should go to 0. That's what we want. I mean the x hat is the collection of our xk hats, our observations. That's the training points. There we really want that those go to this one here. But this is now given by this equation, because I add on this side the derivative of y hat, which is 0. So I take the derivative of ft of x hat minus y hat. This doesn't depend on time, so this is the same as this, but this was minus eta, the derivative of theta ft of x hat transpose times this guy here, gradient of ft of x hat, and then the whole thing is multiplied with ft of x hat minus y hat. Okay, and so we have here a differential equation for this difference here, and it is governed essentially, the derivative is proportional to this thing, and the proportionality constant is this guy here, and of course now it is a constant because this is really what I said before. What I have here is the neural tangent kernel, and this is nearly constant. So this guy here, this is what we call, this is our kernel, and now it's a kernel of x hat comma x hat, and as I said before, this is nearly constant, so in the limit it's constant, so this is proportional to constant. So we have here a constant decay of our f of t, okay, but we should not have a decay with eigenvalue 0, because this would not be a decay. And for this it's also important that this kernel here is really bounded away from 0. So all its eigenvalues are positive, so really we have a decay in all directions. So it's also bigger than delta times identity. And this means that this thing here really converges exponentially to 0. Decays exponentially to 0, or to put it another way, that this guy here converges to y hat. So this means ft of x hat converges exponentially to y hat, or maybe the difference is exponentially going to 0. Okay, and of course we can write down maybe the concrete form of this. Maybe let me also do this. Just solving this equation. This is of course the differential equation for an exponential function, but it involves vectors and matrices. So we should do it in the right form, but it's the same solution as for just numbers. Maybe I just write down the solution of this equation, where I denote this here with k now, and k is a constant, just a constant matrix. Then I have that this ft of x hat minus y hat. This is given, by the starting condition, the initial condition times an exponential function. So namely e to the minus, and this here goes in the exponent, so it's e to the minus eta times t. But then I also have this coefficient here, which is k of x hat times f0 of x hat minus y hat. Ft of x hat is an n-dimensional vector, because I'm plugging in n observations. Okay, and so I get here the gradient with respect to all those guys, but with respect to this gradient, with respect to all those here, I take here the inner product. So what I get here is an inner product for each of the n components. Okay, and so what I get here in the end is an n times n matrix. Okay, so this guy here is an n times n matrix. And this here is an n-dimensional vector. So this here is an n times n matrix acting on n-dimensional vector, and I'm getting out another n-dimensional vector. That's consistent. Good. Okay, and of course you see, I have exponential decay now from the starting condition. So at time 0, I have initialized my neural network. So the f0 makes something out of my my datas, but not the ones which I want. So I have a difference. But now in the time evolution, I mean, this difference goes to 0, because if t goes to infinity, then this will go to 0. If all the eigenvalues of this guy here are positive, but which they are. Good, so this means what I have here, or what this tells me, is that the training error really goes to 0. I mean, the training error is the error which I make on the training data, on my given data, which I put in the beginning. The x1 hat up to xn hat, the little, and the corresponding y's. Those are the guys which I really want to train. At least those should be prescribed correctly by my function. And this here is telling me this. Because this here is telling me what happens if I apply my function to my data, which I had as an input. Good, okay, but of course now, what one wants maybe more to understand is what happens on data on other axes. Of course, the function now does something on other axes, and maybe is this now good or bad? And of course, in general, I cannot say is this good or bad unless I really have a function from which I produced my observations. And then I can ask whether my neural net approximates at least, or is also close to the original function. And so this means for this, I of course I have to prescribe something. Yeah, okay, but maybe first of all we should see what happens on other axes. I mean, this here is somehow the solution for my training data, but now we should look on the solution of this equation for other guys. What can we say there? Okay, so yeah. So what happens with my time evolution? Of course, for t to infinity on, let's say, unseen data, or unseen data axes. So those are not the x1 up to xk hat which I had prescribed in the beginning. Good. Okay. So of course, for those I also have this equation here. Or maybe the one before for the general x. So I have the d ft of x with respect to dt. So this is minus eta. And then I have my kernel. And the first argument in my kernel is now the little x. And the second argument is this x hat here. So this is just this equation here where I'm putting here the x hat. Okay, and then I have here ft of x hat minus y hat. Yeah, okay, so that's the general equation. And of course, we have now, what do we have? We have now, of course, the solution of this guy here. This is just what we calculated, because those x hat here, these are my training data. So this here is minus eta, this kernel x hat, and this was this exponential decay with e to the minus eta t, the kernel of x hat applied to f0 of x hat minus y hat. Good, and so you see I have now here a differential equation again. And yeah, I mean the t is only showing up here. Okay, so this is just the exponential. And everything else is constant. It depends on x, but nothing else depends on t. Okay, and so we can write down an equation, I mean a solution again. So that the time derivative of my function is this exponential function with some coefficients coming out, and so the solution of this, so this is f of t of x. Yeah, so what is this? Yeah, I mean if the derivative of a function is an exponential function, then the function itself is the exponential function, just modified with what I get as the coefficients of t in the exponential. So I mean what I get here is essentially the same exponential function. I just have to see that if I'm taking the derivative, something like this comes out. So let me write it down. So what do I claim do I have here? I have this x hat, And then I have this exponential function, but if I take the derivative of this, then this, the minus eta comes out. This is good, this is here. But I also get this kernel here. I mean, this is the constant, which comes out with respect to the time derivative here. Okay, but this kernel is not showing up here, so I have repair by taking the inverse. And of course, because eigenvalues are not 0, the inverse exists. So I should repair this guy here by taking the inverse. So I take x hat inverse, and then I take e to the minus eta t k of x hat multiplied with f0 of x hat minus y hat. Okay, because if I take the derivative of this, I only take the derivative of this exponential function, and the derivative of this gives me the minus eta, which is here, and it then gives me also the k of this x hat, which is cancelled by this one. And then I just remain with what I have here. Okay, but this of course is a special solution, and then in general I also need, I can add a constant, so I'm adding a constant c. And of course, this constant c I can determine from what happens at time t equal to 0. So if t is equal to 0, then of course, then I get here f0 of x, and then the t is equal to 0, so this term disappears, the exponential term disappears, and I only have here k of x hat times k of x hat inverse times f0 x hat minus y hat plus c. Okay, and so this means I can express the c, the constant here, in terms of the initial condition, f0 of x minus this one. And you see, if I plug then this c in here, I get essentially the same terms as I have in the other. So I can now write the f t of x as, the c is this f0 of x, so let me write this, and then I also have minus this thing here, which I also have here, so let me write this, so I have, in both cases I have the x hat, I have the k of x hat to the minus 1, and I have also the f, maybe I should keep the order, because now those are matrices and vectors. So maybe let me write here the minus 1, and I have here the f0 x hat minus y hat. Okay, so what I have written down here is just the c. The c is f0 minus, this is the minus 1 here, minus this times this times this. Okay, and then I have to add to the c, I have to add this one, but I mean this is more or less what I have. I have this here, I have this here, and then I get this exponential factor, which I put now here, e to the eta t k of x hat minus 1 times this one here. Okay, so this is just taking everything together, and this gives me the ft of x. And now I can see what happens if t goes to infinity, because that's what I really want. That's the end of my training process, what happens there. That's as good as I can get. That's when the training data really give me the right value for the function. So if t goes to infinity, I get my function at the end of training. So this is now this f0 of x here, plus, okay, and essentially I have all those terms, only t goes to 0, and of course I had a minus here, e to the minus eta, which means this guy here goes to 0. And I'm just left with this minus 1. I have the minus 1, but maybe this I do on the expense of exchanging here, writing this the other way. So I put here a plus, and then I have k of x hat times k of x hat. This disappears, and this minus here, this changes this here to y hat minus f0 of x hat. Okay, that's what is happening. Yeah. Okay, and now maybe I have here the initialization, what happens at time 0. This is maybe a bit annoying or makes things a bit complicated, but actually one can get rid of this in a way that at time 0 one really starts here with 0. Okay, so one can initialize the net in such a way that actually I start with 0 and then I get only the effect of the other guys here. Okay, so I don't want to be more precise on this. So by kind of centering, one can get rid of this. One can assume or just restrict to the case where f0 of x is equal to 0. And then my f0 of x, so this is really what my net learns about the function at the point x, is just this term here, k the little x hat, k x hat. Of course, here's a minus 1 of y hat minus f0. Yeah. Okay, and all this f0 I can also get to 0. Okay, so I start with a net where at the beginning f0 is just 0 everywhere. Then I just have this. Okay, so you see I have a quite simple formula, and this actually is a formula which really connects what I'm doing here with kernel methods. So I mean there are kernel methods where you have kernels, and from this you calculate your function like this. So essentially you take, I mean this essentially means that x is just checking how is x, the gradient of x, is this connected with the gradients of your training data. And you try to write this as a linear combination, and then you just take the data which you had from your training data. So I mean, you know everything about the training data, what happens there, and then you have an x which is a different one, and you are trying to write the x as a linear combination of the training data, and this is the output of your function. So in principle, this is still a kind of linear regression thing we are getting here in the end. So still very, very easy, but still also very nice and explicit. Okay, but in any case, we have here a formula now for the function f on any point x. In terms of, this here depends on the training data. Everything here depends on the training data, and here this is where the little x comes in. Okay, and now of course we can ask what is the error which I make on such x's here. And for this, of course, I have to prescribe a function which I want to model. Because I mean, if I just say I have a couple of points, endpoints, and I want to interpolate between them, I cannot say how good or bad are I for points which are in between. It's only if I start with a function for producing those y hats, then I can check whether I'm close to this function or not. And of course, so I mean, what I can take here, and then, okay, one can now try to calculate this in this case and see how good or bad am I. And for this, one has to specify a function, and maybe a function one can specify in this case is that I have a function of a similar type as my neural net, but maybe also allowing some noise. So we could prescribe a model for the unseen data. all datas which I consider. So namely, I'm saying that actually the function is g of x. That's the real function, the function which gives me my data. And this is also of the same type as my neural net. So namely, it is given by an a times a sigma of w times x plus a noise. Yeah, okay, but I mean these a and w's are now somehow prescribed. So let me put a little t there, which now stands for teacher, because the teacher is the one who trains the net. So I have here, I have given here a vector a and I have given a vector w, and from this I calculate my function, but then I also adding some noise, because I mean in measurements I might have some noise. So this here is noise, which is independent Gaussian distributed or so. And that's how I calculate my function. That's my function g, and then the y hats are the ones which I calculate from this function at the points x hat. Okay, and then I let my neural net run, and this now gives me a function f infinity of x, and then I can try to compare what does the neural net gives me as a prediction for the point x, and compare it with this g. And I can ask, is this error small or big? That's the quality of my net. So the test error is then so this is now that I have trained my net, so I get this guy, I get this here, but then I want to test it. How good is it? And this means I'm comparing g of x with what my net f infinity of x gives me, and I want this to be small, let's say in a square norm, and I do this for, let's say, randomly chosen x, and I average over the x's. So I mean I should have, on average, I should have a small, I would like to have a small error like this. So that's my test error. And of course, I mean this e of x, this is now my function g, and the f infinity of x, this is now something which essentially I have a concrete formula which is given in terms of all my input things which I have there. So this is minus k of x at x hat, k of x to the minus 1, the y hat. Okay. And this squared. Okay, and so I mean what I have here is something which in principle I can calculate. It depends now on many things. I mean it depends of course on what I have inputted here. So let's say I choose here this in a random way. This is a random vector, this is also a random guy. So this depends on some random matrices, and this is random noise. And here, of course, this also depends on the randomness which I have put in my net. I have initialized it with some random matrices. So this also depends on some random matrices. So what I have here is, in the end, a kind of maybe complicated, but still some manageable function of the involved random matrices. There are a couple of random matrices involved. Okay, and I mean you have to take expectations and calculate those kernels and so, but in the end this is a kind of function, and actually what kind of function? It's a kind of rational function. It's not just polynomial, not just multiplication, because you also have to take inverses. So it's a rational function of the involved random matrices. So it's a rational function of involved random matrices, which in principle one can calculate. Okay, but maybe to see this, let me say maybe two words. Of course, first of all, I need this kernel here. Maybe that's not so clear. This is a kernel. On what does it depend? And of course, you can calculate this kernel explicitly in this situation. So maybe let us first look on this. So this neural tangent kernel in our setting is actually a kind of explicit object in terms of the random matrices. I mean, that's also what I'm saying here. So maybe that's the main point, which maybe is not so clear. What is this really in terms of the matrices? And maybe we should have a look on this and should note. Yeah, that the kernel, and I mean the kernel is given in terms of the gradient, and so this gradient we can write down explicitly. So I mean the kernel is given in terms of the gradient of f of theta of x, and those guys can be given explicitly in terms of the parameters. And the parameters are the guys which are in the beginning initialized as random matrices. Okay, but so let us look on this. So f, what is our function f? F theta of x. So this was a transpose times our nonlinearity applied to wx. Good. And so what is the gradient of this? So we have to take the gradient with respect to the components of A and with respect to the components of W. So maybe first of all, the gradient with respect to A. So A is just a vector. Okay, so this means I just take the derivative with respect to the A here, and then of course I'm just left with this. So the gradient of this is just the rest here. Wx. So I consider this, I mean, okay, I write this as an inner product, and then if I take the derivative with respect to the ith component of this guy here, then the ith component here is multiplied with exactly this thing here. At the ith component of this. But then if I write this as a vector equation, this just means the ith component here is the ith component here. Okay, so that's just the partial derivative with respect to the components of A. Okay, then what is a partial derivative with respect to the components of W? W is now a matrix. This makes it a bit more complicated, and maybe it's better to write this also in a kind of vector language by saying my matrix is just a collection of vectors, maybe row-wise. Okay, so the question is, what is f theta of x if I take the partial derivatives with any entry of my matrix W? And of course, I mean W is a matrix, but this gradient here, I mean the parameters, I'm thinking of them really as a long vector. I mean the parameters they are entries of a matrix, but I consider this matrix as a long vector. And this gradient here, of course, is just a long vector. It doesn't have a matrix form, even though I take here the derivative with respect to the entries of a matrix. Okay, so maybe in order to understand this better, maybe it's good to write this here in components. So the A, I mean A is just a vector, an m-dimensional, so it just has m real number components, A1 up to AM. But now the W is a matrix, but I also write this as a vector where each entry is actually a row vector. So I write this W as a column vector, but the first entry here, that's the first row of W, but I said I write, okay, vectors are column vectors, so I should take the transpose of a column vector here, and so on. And here, transpose of a vector like this. So W has, W, I'm thinking of W as consisting of just row vectors here. And this row vector, I say the transpose of this is the W1. The transpose of this is WM. Okay, so the WI's here are actually in R to the P. Because W is a matrix, which is P in this direction and M in this direction. Good, okay, and then maybe in this language or in this notation I can write the f theta of x now as the sum from 1 up to m. I mean, this is the inner product. This is ai times sigma of the wi transpose x. Because this here is just, I mean, I'm multiplying here a vector, a row vector with a matrix, and this I can write as a vector where the entries are just inner products between this and the columns of this guy here. Good. Okay, so I can write it like this, and now I can take the derivative with respect to those wi's here. Now I take again derivative with respect to vectors. Okay, partial derivative with respect to vectors are maybe easier. At least I know better what they are than taking it directly with respect to a matrix. So I mean, I take now the gradient of this with respect to w, but this just means I take it with respect to all those entries of w here. So I can now consider the gradient with respect to the wi for fixed I of my function f theta of x. So this is this function here. And now if I take the derivative with respect to wi, then you see I have to take the derivative here. And of course, it's only for, the sum and I only plays a role here. Okay, and then what do I get? I get the derivative of this guy, so I take the derivative of this function, and then I have to take the inner derivative, which is just x. So I mean, the inner function is this here. The derivative of this with respect to wi is just the x. That's as before. So this means what I get here is just the ai times the derivative, outer derivative of what I have there, wi transpose times x, and then the inner derivative is x. Yeah, okay, so this should now be a vector here, which has the same length as the wi. And so let me see, what do I have here? X is here. X is a p-dimensional object. The length of wi is p. Okay, so this x here is p-dimensional, and this here, this is just an inner product. This is just a number. Okay, so this is really this guy here. Okay, so and now, now I have all the ingredients. Now I can write down my kernel. I mean, the kernel is essentially the inner product between this gradient and itself. So if I now take the kernel, this neural tangent kernel, add 2 arguments, so what do I get? I have to take the inner product of the gradient with itself. And the gradient, the gradient has several components. Some components correspond to the a, other components depend to the w. Okay, and then the inner product, of course, is just the sum of the inner product between the a components and the inner product between the w components. So this is just the gradient with respect to the a of my f theta x transpose times the gradient of this. So that's just the first part of my gradient, f theta of x twiddle. But then I have the second part where I have the gradient with respect to my w, and maybe I have split my w into these wi's. So I have said, okay, the long vector coming from the w's is consisting now of a concatenation of vectors corresponding to the wi's, and so I should take here the sum over all i's from 1 up to m of the gradient with respect to the wi. F theta of x transpose times this f theta of x twiddle. Good, okay, and now I can put in what I have calculated before, what those gradients are. Okay, so namely, what is the first guy? The gradient with respect to A. This was just the sigma of Wx. This was somehow the easy part. When my function, I just remove the A. So that's just this part here. So this is then just sigma of Wx transpose times sigma of Wx twiddle. Okay, and the second part from the matrix W, this is now the sum from 1 to m. And this gradient with respect to Wi, this was the AI. Yeah, this was the AI. And I have it twice. I mean, once from here and once from here. So it's an AI squared. And then I have this derivative here. Here's the derivative. I have the sigma prime Wi transpose x, and I have the W prime. Those are just numbers, so I don't care where they. Wi transpose x twiddle, and then I have the x transpose x twiddle. Okay, and again I can write this maybe in a nicer form if I put in here matrices of vectors. So I not just take one vector, but I take several of them. Then again I can lift it essentially by replacing the vectors by the matrices. So the k of x twiddle, where now I have capital X's here. So this is here given by sigma Wx transpose sigma Wx twiddle. And maybe you remember, now you see, this is really what we calculated when we looked on our random features. The random feature model, we wanted to calculate the eigenvalue distribution of this quantity. I mean, I called this f at this point. So this is just f transpose f, and this kernel here, this matrix here really depends on this. Okay, but this is only the first term. So that's what we already looked at. We calculated eigenvalue distributions of those quantities. That's what we understood. But now we get here, because we also have the gradient with respect to this W here, we get an additional term which is more complicated, but still it is given in terms of the matrices. So namely what I have to do here, again I have to replace the little x's, the vectors, by the data matrices. But you see, it's not linear anymore, but it's essentially bilinear. It shows up here and it shows up here. And so if you want to write this in a matrix form, what you have here is actually this matrix multiplied with this matrix, but essentially component-wise. Because you cannot lift things jointly to a big matrix, but essentially you multiply the entry x twiddle entry of this matrix with the x twiddle entry of this matrix. That's usually a matrix product where you multiply entry-wise. That's a so-called Hadamard product. You're multiplying essentially two matrices, but not in a matrix multiplication form, but just that you multiply the corresponding entries. So that's what you're doing here, because here you have the x twiddle entry of this matrix times the x twiddle entry of this matrix. And if you want to write this in a matrix form, then it's not a matrix multiplication, but it's the Hadamard thing. So what you have here is essentially this matrix. This is xt, x twiddle, and then you take this Hadamard product, where you take here the sum of, and you have the other guy is ai squared sigma prime of omega I t. Here you have the matrix X transpose times the sigma prime of WIT, the matrix X twiddle. Okay, and so what you have here is something which contains the matrix X, but the matrix W is split somehow in a way which doesn't look so nice, but you can again write this now as an ordinary matrix product which involves the matrix W and the vector A if you lift somehow this vector A to a matrix by making a diagonal matrix out of it. So this here, this sum here, actually one can write as this guy here, sigma prime. And now I lift this guy here to the W. I'm putting together all the rows of this, then I get this here times x transpose. But then I have to be careful because I'm multiplying this guy here with the AI. And this I can write as a matrix multiplication. If I put the vector, if I make out of the vector A is a vector, it's an m-dimensional vector, but I can transform this into a matrix, a diagonal matrix, where I'm putting just the vector on the diagonal. Everywhere else is 0. And then I have here sigma prime W x twiddle. And then you see again I have written things very nicely in terms of my original matrices. I mean in my model for this neural net, I had the data matrix, which we assumed as a Gaussian random matrix. We had this W matrix, which we assumed as a Gaussian matrix, and we had this vector A, which we also assume as a Gaussian random vector in the beginning, and now I make this to a matrix, so I have here also a kind of matrix which has a kind of Gaussian behavior. Of course it's diagonal, but I have written it in a very compact form in terms of the matrices which I have here. So similar as here, but now it's getting more involved. I also need information which involves the A. But in principle, it is given in terms of my original matrices. I mean that's the main thing what I want to say here, that this quantity here, which depends on my kernel, really can be written in this form. Essentially it is given in matrix operations of my original matrices. And if I do this calculation here and I take the expectation, then I'm also taking traces of such things, and I'm going back to things what I want. And maybe the final point is that we also have this nonlinearity here. So you apply nonlinearity to a product of two independent Gaussian matrices, and that's what we saw in the chapter before, that such a situation, that such a matrix, the nonlinearity, a nonlinear matrix of such a product can actually be also replaced by just a linear, just by this product plus adding independent noise. So I mean, nonlinearities are not so clear how to deal with them directly, but essentially we have seen we can replace this by getting rid of the nonlinearity, but then adding another matrix. And then I'm just back to having product and sums. That's, again, I essentially go back to rational functions. The nonlinearities disappear because I can replace them by adding other random matrices of the same Gaussian type. Okay, and the kernel here also just involves products and sums of my matrices and nonlinearities which I can get rid of. So in the end, this whole thing can be reduced to a rational function, maybe a bit complicated one, but in principle it can be done explicitly to a rational function of the involved random matrices. And if you want to calculate this average, essentially you have to understand the eigenvalue distribution of those matrices. You have to calculate the Stieltjes transform. Okay, and so that's maybe the essence of what I wanted to say here, that you can at least calculate something in those models, reducing it to the calculation of eigenvalue distributions of rational functions of Gaussian random matrices. And then of course the question is, can we calculate something like this? We looked on examples where we had the product of two matrices, for example. So where I showed how you can do this kind of explicitly, but now the question is, can we do more complicated situations? And that's something about which I want to talk a little bit more. I mean, yes, we can. We really can do something in this direction. And that's actually, I mean, this tools for doing this are actually provided by free probability theory. That's a subject on which I'm actually working. And maybe I want to give maybe in the next few lectures at least a little bit in this direction, and give an idea how we can address this, because this is something which in this context is important. So I want not to give an introduction to free probability, but maybe an idea how for polynomials, let's say, or even rational functions of random matrices, one can maybe do what we did before in very specific situations, do in a more general, more conceptual way. Okay, but this will come maybe in one or two of the next lectures. And then maybe I should also say a little bit more on the neural tangent kernel. Why is it maybe constant in time and things like this? So those are things which I still want at least address a little bit in the coming lectures, in one or the other order. I mean, I'm not yet decided how much I will say about what, but at least those are the things which I still want to address in the last 2.5 weeks. Good. Okay, that's it for today. Thanks.